Okay, so yesterday we talked about the area function drawn on the board. Where's my magic pen? Come on now. Let me see my magic pen. It's right here. Oh, there it is. What? Good eye. Okay, so we talked about this area function where we define an area under a function with a variable upper limit, right? And we asked the question, how could we define the rate of change of this function? And what did we decide? Well, if the function is, well, you guys tell me, what did we decide? What determines the rate at which the area under that curve is changing?
The height of the function.
The height of the function. Right, now because we're sweeping out area at a constant rate, right, as x is just changing linearly here, right? So as x changes linearly, it's not varying from here to here. The only difference is here the function is taller than it is here, right? And so we ended up with the result, the second fundamental theorem of calculus. The rate of change of this area function is based exclusively on the value of the function at x, okay? And we looked at an example using a function we don't even know how to deal with. We don't even know the calculus of this function, but it doesn't matter, right? If we define the area function as the area under the function natural log t from -11 to x, then the rate at which that's changing is just natural log x, right? Okay, but we left off talking about, and there we proved that it works, right? We use the shortcut, which is really short, or I guess there's the shortcut, or we powered through this thing actually doing the calculus. But sometimes we can't even do the calculus. There are some functions, I'll give you an example while we're on the subject. Like if I were to, which one that wouldn't be defined? Okay, I don't want to. So we could do something like this. What if we wanted to, we define the area function as the integral of cosine x squared dx from -111 to x. Well, I could call those x's, but I won't. We'll call them t's just so we don't get confused. Oops. Right, so we'll use our dummy variable. What's the point of the dummy variable again?
Just organization.
Say it again.
Organization.
Yeah, kind of. I mean, it's just because all it's doing is giving us we have to put an input variable into the cosine, into the function to know what the landscape looks like, right? But this determines how far we've walked along the landscape, right? Okay, so if I want to find f prime of x this time, I don't have an option because, why doesn't everybody put all your distractions away? Because this is not an integrable function. You can't analytically take this antiderivative. It doesn't exist mathematically. So you couldn't do this. You couldn't do this the hard way. You couldn't actually calculate the antiderivative and then calculate the definite integral and then differentiate it, because the definite integral, the antiderivative doesn't exist. Yep.
Is that a t squared?
Yeah. Yeah. That's what makes it different. If it was just cosine t, obviously we can do that. But if it's cosine t squared, I'm pretty sure that's one. Yeah, that one's not. You can't take an antiderivative of that. But using the second fundamental theorem, the answer is easy. What's the answer? No. No, the derivative of that area function is
Cosine t squared.
Cosine x squared, right? So we bypass a bunch of non-existent calculus there, so it's a good shortcut, right? Sometimes it's the only method. Okay, one other issue though. What happens if we're sweeping out area at a non-linear rate? Okay, that changes things, doesn't it? Right? Because now as the input variable is increasing at a rate equal to the square of x, not just x, right? So when x is 1, we're only adding up the area from a to 1. But when x is 2, we're adding up the area from a to 4, right? And so as x increases, what's going on? Well, if we watch this thing sweeping out area, it would be doing that. It's accelerating, isn't it? Right? So does it make sense now that the rate at which the area is changing is not only dependent on the height of the curve, right? It's also dependent on the rate at which we're gathering up area or sweeping out area, right? Does that make sense? So we got to have something else here too, right? What do you think that's going to be? The rate at which we're accumulating area. How are we going to do that? Any suggestions?
More vertically sloped.
So what you're getting at there is you're concerned about, once again, ultimately the height of the function, right? Agreed? And that part we've already dealt with effectively, right? We know that it is dependent on the height of the function. So if I was going to write down, we're going to have to fill in some blanks here, but we could say if the derivative with respect to x of the integral of f of t dt from a to, we'll call this, what do I do on my sheet? I want to make sure I do the same thing. Do I do g? Yeah, that's good. Okay. To some function of x, right? In our case up here, it's x squared, but it doesn't have to be. It could be any function of x. What's that going to equal? So we get the idea that it's going to be f of what in this case? G of x, yeah, right? Because we're actually going to be plugging in x squared into the function and not just, does that make sense? Mm-hmm. When x is 4, the upper limit is not 4, it's 16, right? So that's what we're evaluating the function at. So there's one important difference. So it's going to be f of g of x, but that's not enough, right? Because we're also sweeping out area at a nonlinear rate. Well, what do you think I have to multiply this by? Because it's going to have to be something...
By 4.
By what?
4.
Not 4 necessarily. F of x. Okay, we're on the right track. But when f of x is 4, then x squared is 16, right? But are we really multiplying by x squared? Because if I multiply by x squared, that pays attention more to the total amount of area under the curve, doesn't it? See what I'm saying? It's like, let me say it this way. Like if I'm accelerating, okay, so if I'm accelerating at a rate, I want to give a good example here. Okay. I can't think of a good analogy with. Okay. Okay, here, think of it this way. So if I'm accelerating, let's say that on a trip, I'm starting from Pendleton, and I'm driving very slowly along the freeway, right? I'm gradually picking up speed. And so we're saying that every hour, I'm going to maybe double my speed, right? So if I start off at 1 mile an hour, I'm not going very fast, right? I'm only going a tiny bit, but after an hour, I pick it up a little bit. So at some point down the line, actually, I'm doing that wrong. Every hour, how am I going to say this? Every hour I will have, it's not working. I gotta think here. Yeah, okay, every hour I will have gone, the outer number of hours is t, I will have traveled t squared distance. This will make it work. Or we can even do minutes, let's say, right? So I'm going pretty slowly initially, right? After 1 minute, let's say I've gone, we're maybe talking about meters. They're down at kilometers, yeah. So then after 10 minutes, I will have gone 10 squared meters, 100 meters, right? Still going pretty slow. After 100 minutes, I will have gone 100 square meters. You get the idea? Okay, this one will work. So then, am I going to multiply the height of my function, right? Am I going to multiply that by 100, by the distance I've traveled? No, I'm not really, am I? I can't multiply by x squared because that's the accumulated distance I've traveled. What am I really going to multiply by?
The value that you're currently at, the x value.
Not the value I'm at. I'm more interested, I'm looking at the rate at which I'm adding area, right? Or in our car case, the rate at which I'm accumulating distance. So it's right, the square tells me how far I've gone.
Is it just by x?
But I'm not really interested in the distance I've traveled. I'm interested in almost.
T, yeah.
We got that part, right? We got the f of g of x to f of x squared part, right? So that's the height of the curve. But yeah, and the bull will come on in a second here, but you gotta get it yourself. So the height is increasing. You're seeing this part, that the height is going up non-linearly, right? Because I'm plugging in x squared into the function instead of just x, right? But as I'm traveling down the road, I don't really care about the total distance I've traveled when I want to know the rate at which I'm traveling. What is it?
F prime of x.
F prime of x. Yeah.
That's the speed that goes.
You see what I'm saying? We want to know the rate at which that upper limit is changing. You see what I'm saying? We're not interested in the total value at which I'm evaluating the function. When we're talking about the rate at which we're sweeping out area, we want to know how fast is that upper limit changing, right? Not what its value is. We said yesterday, and I think this made sense, that we used a similar analogy, and if we want to know how fast we're going at any instant in time, it didn't depend on how far we traveled, right? It was independent of how far we traveled. All that mattered was, at that moment, what was the rate at which we're changing distance, right? So what we got to multiply by here is not f of x, or g of x, sorry. We got to multiply by the rate at which that's changing. How fast is that upper limit accelerating, right? See what I'm saying? How fast, what's the rate at which g of x is changing? Because that's going to tell us about the rate at which the area is increasing, not the absolute value. We don't care about the value of that. We just want to know how fast is it increasing or decreasing, right? So we're going to multiply through by g prime of x. Now, if we look back at our previous example, we really didn't even think about it, but we did that, right? If we go back to there, well, we really did that. We said that if we want to know the rate at which area is increasing, we need to know the value of the function at the upper limit, right? But we also need to know the rate at which the upper limit is changing. But what's the rate at which x is changing with respect to x? dx dx is just 1, right? So we're sweeping out area at the constant rate of 1, whatever we're measuring, 1 unit of x per unit time, for example, right? Okay. We're changing t at a rate of, 1 unit of x per unit of distance along the x-axis, so only 1. We're just multiplying this whole thing by dx, which is just 1, right? We just kind of took that for granted, though, right? We never really addressed it specifically, and we were right to do that. The only thing that really mattered here was the height of the function, because we were sweeping out area linearly, right? Okay? So when we get to something like this, this is much more sophisticated. Now we got to multiply through by the rate at which the upper limit is changing. Okay? So let's do an example. And you'll see that this is, I don't think this is in the book. I don't think it is. But it works. Just trust me, it works. I don't think it's in the book. I don't think it is. But anyway, it's one that you ought to remember. I'm in the process of putting all of just everything we've talked about. I'm putting on I made a new section on the Calculus Moodle page called Calculus Handouts. And everything we've done, I'm just kind of trying to put some stuff in there. So you can use it, eventually when we get ready to have a final. But also, when you go to college, if you want to just keep your accounts, you can go back and draw on these resources when you're taking college calculus too. So let's try an example. What if we had something like this then? What if we had f of x is an area function defined as, let's say it's going to be sine t dt, and we want to know the rate at which that's changing as x goes from -5 to x cubed. Okay, what's the rate of change of that area function? You don't really have to do anything. You're just applying that second fundamental theorem.
Sin x cubed
Times
3x.
3x squared. Yeah, that's it. So we'd probably simplify that to be 3x squared sine x cubed, but that's it. Okay. All right, now I got one more for you. We're going to take this one other large step well beyond what our book does. This is kind of useful. Trust me, in the future this will be useful. So what if we did something like this? What if we defined an area function where the area is changing on both the upper and the lower limits? So if we did something like this, let's say we're going to define f of x as, integral of, in fact, let's just be totally general. It's going to be f of t dt from h of x to g of x. Any ideas how we could treat this one? And use, and base our approach to this new kind of area function on what we already know. Okay, what do we already know? Well, we only know at this point, we've only dealt with area functions where we have a constant lower limit. So how could we take, this generalized second fundamental theorem and turn it into the ultra generalized second fundamental theorem, where we've got area functions depending on variable upper and lower limits? So this is a pretty wacky area function, right? So the left edge of the area function is changing non-linearly, and so is the right edge, so maybe it's doing something crazy like that. But we want to know for any given value of x, right, at what rate at that moment is it changing? Idea.
Be divided by the h prime.
H prime.
So we're gonna probably have to have an h prime in there too, right? what could we do? Let me ask you this, do we have any properties of definite integrals that would allow us to deal in a convenient way with these kinds of limits of integration? Could we write this in terms of something we're familiar with, which is an area function where one, either upper or lower limit, for us just the lower limit, is constant, right? Yeah, I'm going to remind you of something. Like, what if we wanted to, okay, so the integral of f of x from 1 to 7 is equal to 11. The integral of f of x from 3 to 7 is 7. I want to know what's the integral of f of x from 1 to 3. What's it going to be?
4.
How'd you get that?
It's just, the last two added up equal to
Okay, but how would I,
11 19.
okay, and how are you getting that, Brent? So I'm going to take, it's the integral of, what am I starting with? The integral, which one of those do I start with? Okay, so the integral of, okay, 1 to 7, or I could say plus, if I wanted to, plus the integral from, if I want to end up going from 1 to 3. 7 to 3, good. Right? Does that make sense? What did we really do there? Well, we added up the area from 1 to 7. Right? So we added up the area from 1 to 7. Plus the area from 7 to 3, right? Which means we're going to be going, so this one moved in this direction. Now we're going to add up the area from 7 to 3 in that direction, and that's going to leave us with that area, right? As long as those two limits match up, it has to work. Okay, so, right, but maybe we could do something like this, right, where this is h of x, and this is g of x, right? So h of x and g of x, right? And in between, does that have to be something that's a function of x? No, that could be, see what I'm saying? That could be something that's constant, right? Get the idea? Okay. And just to finish, yeah, it could be like 0, sure. Like pick a value, like could be 0 or it could be any constant for that matter, right? Wouldn't even have to even specify, would we? Right?
Just put 8, right?
And it's, I know this might seem weird, and the reason I made this example is because 7 is bigger than 3. That's all right though, right? I'm still just adding up a positive area plus a negative area is going to give me what's left over. This value doesn't necessarily have to be between 1 and 3. It's still going to work, right? And how come? Because if I look at the numbers here, what do we define? So this one we defined as being 11, right? Plus, if the area under f of x from 3 to 7 is positive 7, what's the area from 7 to 3? Negative 7, right? That's a property we have. So I get 4, right? Okay, so now let's go back and look at this possibility then. So we should be able to do something like this then, right? We should be able to say the area under f of t dt from h of x to a. Just make it a constant. Could be 0. right? Plus the integral of f of d dt from a to g of x, right? Okay, well that looks really familiar. That's just our current second fundamental theorem, right? What do I need to do to this one to make it look like the one that we know now? Because the lower limit was the limit that was constant.
Make it negative.
Make it negative, yeah, right? All I have to do is flip this one around. Right, I could write this as negative the integral of f of t dt from a to h of x, right? Plus integral from a to g of x of f of t dt. And maybe I flip those around so the positive one is first, right? And that's pretty trivial. It's not like that's essential, but it'll make things maybe a little bit easier. And now, those are, I can deal with, right? Those are exactly what we did before. So what's this first one going to end up being then? What is this whole thing? So if this is my, let me say this again, this is my area function, right? This is what we called f of x, right? So now what's f prime of x going to be? What's the derivative of that one? Good, f of g of x times g prime of x minus, how about this one?
H of x.
Times, oh, there it is. There's the ultra generalized second fundamental theorem of calculus, a room 304 exclusive. Okay. All right, so let me print this guy off. Well, maybe I already did. Oh, I might have already done that.
Okay.
Very colorful.
Christmas
Mm-hmm. Only better.
Wait, no.
Get it to half. Snap it in half.
Yeah, yeah.